It's been said that there will always be prayer in school as long as there are word problems in algebra. And a classic was the train passing problem, which usually has some information about the speed, distance, and you go and figure one or the other out. And it comes as no surprise that one can find on the internet, here the math forum, a number of examples meant to help students in their computation of the train passing problem. And let's do an example. And consider, if you will, you've got a train that goes 30 miles an hour and another one going the other direction at 60 miles an hour, and they're 15 miles apart. And the trick here is to recognize the remaining distance for one train is the distance for the other. And you substitute through, and sure enough you get, one is going to be 5 miles, the other one is 10 miles, and the time is at 1/6 or 10 minutes. And indeed, that is possible if you happen to know the distance between the trains. And, let's see, here's a schedule here from an Amtrak train. Wait a minute, it doesn't show the speeds, but we could probably figure it, not taking into account the stopping and starting and the intermediate speeds. But wait a minute, we can simplify this. And by simplify, I mean that we no longer have to enter the speeds or calculate them, or even the distance. All we need are the arrival and departure times. And here we just note that we're going to assume that the fraction of the distance for one train will be the remaining fraction from one, 100% if you will, for the other, and set them equal. And the trick here is to take the fractional proportions, which would be the same when they meet each other, substitute that into the other equation, and solve. And it turns out the time is determined by the product of the arrival times minus the product of the departure times, divided by the total length of journey for each train, that is the arrival times minus the departure times. Time for a couple of examples. Let's have a fast train and a slow train. Think about it. Trains going downhill usually have to go slower to conserve their brakes. And we have one leaving at 1 p.m., arriving at 4. We'll see it's the faster one. Another one leaving at 3 p.m. and arriving at 9 in the other direction. And we substitute it in, and we find that it will pass each other at around 3 2/3, or that's to say 3:40 p.m. And if you happen to have the distance, you could then calculate that as well. And I should note that this is of interest for more than one obvious reason. Maybe it's nice to know when they pass, to take a pretty picture, or indeed for planning, so you know where to put in sidings, passing tracks if you will, if that is necessary, where the only one track is normally available. And in fact, you can see these sometimes, especially in McDonald's in Eastern Europe, where they put them on the sides of the walls. Here we have another example. A train leaves at 8:10, arrives at 8:50. Another train leaves at 8:20, going the other direction, and arrives at 9 o'clock. Turns out, by the way, these happen to have the same speed or travel time. We'll see how that becomes interesting. And you work that through, and indeed I just show the total of the travel times there in the denominator, and it turns out it's 35, or doing this in minutes, or 8:35. And again, notice, we never had to look up the mileage. We didn't have to compute the speed. And these are of interest because we can know where to get ready to take that photo of the train coming the other way. It's great for planning purposes if you happen to have reasons to know when to schedule trains. And, a simplification of a problem that was made unnecessarily hard.